This should be fun today. F.T.A. F.T.A. I wonder what F.T.A. stands for. Future Teachers of America. No. Fairmont Track Athletes. Maybe. What else could it be? Firebirds. Thankful Always. I don't know. I don't think that's what it is either. I wonder what it's going to stand for. Well, today, let me tell you what this is going to stand for. It's going to stand for the fundamental theorem of algebra. Today is going to be the fundamental theorem of algebra. Okay? This is actually one of the last lessons in Chapter 2. So, without further ado, let's get going on this and finish up this quarter strong. So, here we go. So what I have here for you is I have a bunch of graphs. So you'll notice over here I've got 4 different equations, functions, and they're color-coded. I got a red, a blue, a green, and a purple. And over here I've got, of course, the 4 graphs. So I want us to go ahead and look at these, okay? So here, when I look at this, I have 2 different factors. Okay, actually, let's do it in matching colors. So here I have 2. That's not red anymore. I forgot I don't have a red one. That's okay. We do now. This is 2 different factors. Boom, boom. Okay? Now I want you to look at that. Those 2 different factors give us 2. Why did it do that? Give us 2 different zeros. 2 factors, 2 zeros. We'll just go ahead and stay with what we have. Okay. There we go. We got 2 different factors, and we have 2 different zeros. Look at this next one here. This next one has 1 factor. Has 1 factor. Happens twice. It happens twice. This is x plus 3 and x plus 3. Okay? And I want you to look at the blue graph. It intersects the graph only once. That's weird. Alrighty. Let's look at number 3 here, this green one. Okay, the third one here has 3 factors. Has 3 factors. Now it happens, this one happens twice. And this one happens once. Okay? So let's go over to the graph. It has 1, 2 x-intercepts. Alrighty, let's look at this last one here. This last one's in purple. The last one's in purple. Okay, so this has a total of 4 factors. This one happens 3 times. And this one happens once. And if I go over to my graph, here it is, the purple one. It's here and here. Okay. Now there's a reason I'm doing this, because I want to look at the relationship between the factors and what the graph is doing at the zeros. Okay? So here we go. We're going to go through this again. So let's start with the first one here. Here I had 1 factor of each. What is my graph doing here? My graph at those locations is crossing over, it's passing through the x-axis. Okay? So for these right here, so for the red one, I'm going to put it right here, red. Okay, at x equals -2 and x equals 3, those will be the zeros, right? The graph crosses the x-axis. It's crossing over. It crosses over the x-axis. That's here and here. Okay, let's go to the blue one. The blue one has zeros of x equals -3, and that actually happens twice. Now, why does it happen twice? Well, each factor would give me a 0 of -3. So what we would say is, if we want x equals -3 with multiplicity of 2. It means it happens twice. So let's look at it here. What do we notice about the graph? What is it doing? It doesn't cross over. It just does what? It touches and turns away. Okay? Here, I'm going to call it a turn and, I'm just going to call it touch and turn. Touch and turn. Touch and turn. Boom. See it? The graph comes down, touches the x-axis at the 0, and turns away. All right. Let's go to the green one. Let's see what's happening here. Okay. So how many zeros, how many unique zeros do we have for the green one? Let's see what we got here. So for the green one, this is going to be x equals 2 with multiplicity of 2. And an x equals -5. All right, so let's look at x equals 2. Here's x equals 2. Look what happens when it had a multiplicity of 2. At x equals 2, touch and turn. Oh, at x equals -5, it crosses. Do the last one, and let's talk about what's going on here. So the last one here, let's make this a little bit longer here. I'm going to extend this page, okay? So at the purple one, our zeros here would be x equals 3 with multiplicity of 3, because it had to factor 3 times, and x equals -8. Okay, what's happening at 3? At x equals 3, here's x equals 3. What's the purple graph doing? It's crossing. And at x equals -8, right here, it's crossing. So why does it, sometimes it crosses over the x-axis, this purple one, this red one, this green one, this purple one, this red one, and then sometimes it touches, the blue and the green, these two touch. They touch and turn. So how do I know what my graph's going to do at the 0? How do I know if it's going to cross over or if it's going to touch and turn? I think some of you know. Here it is. Okay. If a factor, okay, let's say a 0, okay. If a 0 has an odd multiplicity then the graph crosses the x-axis at the 0. An example. So an example would be if you had x minus 5, and this was cubic. This would mean x equals 5 with multiplicity of 3. 3 is an odd number. That means I know that at x equals 5, this graph is going to be crossing over there. It's going to cross over. I know that for a fact. Okay? The other version then says if a 0 has an even multiplicity then the graph touches and turns at the 0. That's what I know now. It's going to touch and turn at the 0. So an example here could be something like this. If you had x plus 3 quantity squared, that would mean at negative 3 right here, this graph would do this, touch and turn. So this type has to cross over, okay, and this type is going to touch and turn. Understanding what the graph does at zeros based upon the multiplicity of the 0. How many times does that 0 happen? Or how many times does that factor happen is what it's all about. Okay. So, fundamental theorem of algebra. That's what F.T.A. is. Fundamental theorem of algebra. Here's what it says. A polynomial with a degree of n must have a total of n solutions, which includes all repeating zeros. Repeating zeros. The total number of zeros can be comprised of real and imaginary values, and some might repeat. So, what am I saying here? If f of x is 5th degree, it must have 5 zeros. Has to have 5 total zeros. It doesn't mean it has 5 unique zeros. It could have 1 0. I could say, oh, it has 1 unique 0. 1 unique. Still has 5. Here, x plus 2 to the 5th. That has 5 zeros, but it's just 1 unique. X equals negative 2 5 times. What if I did one like this? Here we go. X cubed times x minus 2, the quantity squared. This would be a 5th degree polynomial. Okay? It would have 2 unique zeros, but it still has a total of 5. It would have 3 at 0 and 2 at 2. So but I know it has to have a total of 5 zeros altogether. Okay? So this is what we're talking about. The fundamental theorem of algebra says whatever the degree of a polynomial is, that's how many total zeros you must have. And some of those zeros might repeat, and some of the zeros could be real, and some could be imaginary. Our job today is to be able to work with that concept. So let's try this. Here we go. I want to solve the following. Solve for all zeros. I want to find all the zeros there are. Okay? So f of x equals x cubed plus 2x squared minus 5x. Now when we solve these, what are we going to do? Let's make this plus 5x. That's okay. Doesn't matter really. But what are we going to do when we do this? Well, here's what we're going to do. We're going to factor, which is what we've been doing all along, factor this. Okay, GCF x times x squared plus 2x plus 5. Boom. And then this is equal to 0. Great. There it is. Now, what do I know? I am multiplying two factors and getting 0. So x, my first factor, x equals 0, and x squared plus 2x plus 5 can equal 0. So one of my solutions is this. Boom, it's done. X equals 0 is a solution. What do I know? It's happening one time. That means I know the graph is going to cross over the x-axis at x equals 0. Let's do this one now. Here we go. How do I solve it? It's quadratic. Factor it, square root property, or quadratic formula. You could try factoring it, but you're not going to be able to. So this is a quadratic formula. Okay, x equals negative 2 plus or minus the square root of b squared minus 4 times 1 times this, boom, 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 all over 2. X equals negative 2 plus or minus the square root of. In here, you're going to get negative 16. Negative 20 and 4 is negative 16 all over 2. That's negative 2 plus or minus 4i all over 2, which means x equals what? Negative 1 plus or minus 2i. Now that's how many zeros? That's 2 zeros. They're imaginary. Negative 1 plus 2i, negative 1 minus 2i. So I have 2 zeros here, 1 0 here, that's 3 zeros. It was a third degree polynomial. Boom, I have them all done. Have them all done. 1 real, 2 imaginary. Total of 3 zeros. That's our goal, to be able to find all zeros, both real and imaginary. Let's try another one. Let's do this. Here we go. Okay, so I want to do this one now. It's quadratic. It's quadratic. So let's try to factor it. Yeah, it's not going to factor. So it's just a quadratic formula problem. Quadratic formula. Okay, x equals negative 2, so 2 plus or minus the square root of b squared, 4 minus 4 times 1 times negative 7, all over 2. That's x equals 2 plus or minus the square root of. Here it's going to be 4 plus 28, which is 32, all over 2. Remember, if you get to that point, that's still a good answer. I'm going to go a little further. X equals 2 plus or minus. This would be 4 radical 2 over 2, which means x equals 1 plus or minus 2 radical 2. So there are 2 zeros. 1 plus 2 radical 2 and 1 minus 2 radical 2. Okay. Boom. 1, 2 zeros. It's quadratic. The number of zeros is the same as the degree of the polynomial. Notice, I didn't say the number of unique, different. I never said it's the number of different zeros. It's the number of total zeros. Repeating and non-repeating. All right. So here we go. Let's try one more here. What if I told you the following? If f of x has a 0 of, let's see, what do I want it to be here? How about x equals 3 minus radical 5? Now let's think about this, okay? If f of x has a 0 of x equals 3 minus radical 5, I want you to go back and look at what happened here. When I had 1 minus 2 radical 2 as an answer, look what else happened to be an answer. 1 plus 2 radical 2. So what do you think would be true? If 3 minus radical 5 is an answer, guess what? Then, so is x equals 3 plus radical 5. Look at this. then this is, if this is true, so is this. Now, what do we call those two numbers, this and this? Who remembers? Those are referred to as conjugates. Conjugates. Remember, the first term has the same sign. The second terms are inverses of each other, the opposites. Okay? Those are called conjugates. So this next thing is very important. Okay? It is known as the irrational conjugates theorem. Irrational conjugates theorem. And here's what it says. If a polynomial has an irrational zero of x equals, and I'm just going to use letters here, okay, a plus the square root of b. Okay, if I know that a plus the square root of b is a 0, then x equals a minus the square root of b must also be a 0. Okay? So what this means is this. Irrational zeros happen in conjugate pairs. Irrational zeros always happen in conjugate pairs. All right. So, what do I know? If x equals 2 plus the square root of 3 is a 0 of f of x, so is x equals 2 minus the square root of 3. And if I told you f of x is quadratic, which means it has a degree of 2, you then could find the polynomial. Because you could say, oh, x equals 2 plus radical 3, x equals 2 minus radical 3. These are my zeros. This factor is x minus 2 minus radical 3. And this factor is x minus 2 plus radical 3. And if I wanted to find f of x, I would just take those two and multiply them together. So I could take the zeros, write them as factors, and multiply them out to get my function. All right. Yep, that's what I could do. Okay, so I want to go ahead. Let's do one more here. So we're going to do another problem here, and let's see what happens with this one. Okay, so I'm going to tell you, I wrote this problem down over here. I've got g of x, and g of x equals x cubed minus 2x squared minus 5x, or plus 5x, and minus 10. Okay, I want to solve this. I want to solve this one. Solve. All right. How do we solve this one? We try to factor it. It's cubic. What do I notice? It's got 4 terms. I'm going to try to factor by grouping. GCF here is an x squared. GCF here is 5. Oh, look at that. So I've got x minus 2 and x squared plus 5. Boom, there's g of x. Set that equal to 0. So what do I know? X minus 2 equals 0, and x squared plus 5 equals 0. So x equals 2, x squared equals negative 5, x equals positive negative I radical 5. How many zeros? 1, 2, 3 zeros. It was a third degree polynomial. Perfect. One of them's real, 2 are imaginary. I want you to look at these two imaginary ones. This is plus I radical 5, and this is minus I radical 5. Guess what number's in front of these? 0. Guess what these are? These two are what? Conjugates. They're conjugates, and they're complex numbers. They're complex conjugates. So not only do irrational zeros happen in conjugate pairs, so do complex zeros. And that is known as the complex conjugates theorem. Okay? Here's what it says. If A plus BI is a zero of a function f of x, so is a minus bi a zero. Okay? So this is telling me then complex zeros of a polynomial happen in conjugate pairs. They happen in conjugate pairs. Yep. All right. So if f of x has a zero of x equals 3 plus 2i, then f of x has a zero of, x equals 3 minus 2i. Again, notice the first term, the signs are the same. The second terms, they're additive inverses. Those are complex conjugates. Okay. Woo, you guys are doing great. Doing great. Few more problems. Few more problems and we're almost done. Here we go. So this is what I want you to be able to do. Write a polynomial function. Let's see. With least degree and zeros of x equals 2 and x equals 3i. So if I want it of least degree, now let's look at the things I've got here. Okay, so I've got x equals 2. X equals 2 is a real number. It's a real number. So this could happen a minimum of once. One of those. Here I have x equals 3i. It is a complex zero. If x equals 3i is a zero, then I must also use O. And I must use x equals negative 3i because they have to happen in conjugate pairs. So I'd have a 0 here and a 0 here. That means the least degree of this is going to be a third degree polynomial. So I know this is going to be a third degree polynomial. Once I know that, write my factors. My factors, x equals 2 is going to be the factor x minus 2. X equals 3i is x minus 3i. X equals negative 3i is x plus 3i. This is going to be my function f of x. There it is. I can't leave it like that. I have to multiply it out. Start by multiplying these factors. They're what? Conjugates. The middle terms will drop out. When you multiply these, you get x squared. Here you get minus 9i squared. Woo! Remember, I squareds can't stay I squareds. They turn into what? Negative 1s. So this really becomes x squared plus 9 times x minus 2. Now I can keep going. Now I keep going on this. What are we going to get here? Take the x squared through. You're going to get x cubed minus 2x squared plus 9x and minus 18. There is a polynomial that has zeros of 2, 3i, and negative 3i. So now I have my polynomial function that meets the criteria that I was supposed to up here. Met the criteria. All right. Let's see here. I think I have a question all ready for you guys. Oh, wait. No, let's do this. I think I have my question written down here. All right, what if I want to do the following? Answer this question for me if you would. Can a fifth degree polynomial have, here we go, one positive zero, one negative zero, three imaginary zeros? Can it have those things? Can it have those things? Can a fifth degree polynomial have one positive, one negative, and three imaginary? Hopefully your answer is what? Well, yeah, this is good. I can have this. This is okay. What about three imaginary zeros? Can I have three imaginary zeros? And the answer to that is no. You can't have three imaginary zeros. It's impossible. Because if you have one imaginary zero, its conjugate also has to be. So if you have imaginary zeros, it will always be an even number of them. So this is not possible, this part right here. This is not possible. Whew. All right. Guess what? It's homework time. Homework time. Here it is. This is what I want you to do tonight. Page 141. Numbers 3, 5, 7, 11 through 19, odd. 21, 25, 27. Here, I believe these are where you're going to write a polynomial from the information. 43, 46, and 65. Boom. That's your homework tonight. Good luck, and I will see you later.